Okay, the sensor data, so the input data of the whole platform. So we have different type of sensors. So one is the Raspberry Shake 4D, which has been mentioned already several times. So this is a low-cost sensor, which is based on a vertical geophone. So it's a velocity data it's generating, and we have three components, three strong motion components. So that is here, the top one. They come in different casings. So this is the home enclosure, which we purchased in this project because most of the test beds designed their own casing around that. I have also some sensors in the hall. There's a small booth, so we can go more in detail there. So the second sensor we have is the GNSS sensor from Yet It Moves, and they are in some sites co-located. So the GNSS sensor is generating the raw GNSS packages, and the Raspberry Shake sensor is extended with a functionality which can transmit not only the seismic data, but also the GNSS data. So these two data types are finally forwarded to the acquisition platform of TURNkey, and from there it's going on into the either seismic processing or in the GNSS processing. I think Benedict, so in the next talk, has a few more slides on that topic. So the other type of input data is the mobile app, so the Did You Feel It reports, which are collected by EMSC or the University of Bergamo, and they are transmitted to their to the local servers, so at EMSC and at the University of Bergamo. And one of the developments within this project was the extension of our so-called Quakeling server, that it can handle also Did You Feel It data. So normally it was designed to transmit earthquake information either in real time or in time windows, but in this project it's extended that we also get the Did You Feel It data in real time transmitted. So similar to a seismic data stream, we get a Did You Feel It data stream here. So and everything is integrated into the TURNkey platform. So this data is processed with the SeisCom framework. So that is the seismic automatic processing system. And from there, first results like earthquake early warning products or also earthquake parameters are generated and then handed over to the TURNkey engines or applications here. So here's just a picture of the network with the different test beds here. So Iceland, Groningen, Netherlands, France, Romania, Greece, and Italy. So this is just showing the different stations. In total, there are about 100 stations set up. I think even a bit more because people also purchased additional sensors or put their own sensors in addition, which we also integrate. So it's not only the TURNkey sensors, but it's also sensors of the national networks, which are integrated and complement, let's say, the conventional TURNkey network. What we have here, okay, so that is not a conventional network. So this is now the results of this whole Did You Feel It acquisition and processing. So this is the earthquake on the 22nd of April in Bosnia with a magnitude of 5.7. So there's a complete cluster of earthquakes. So it's not only the main shock, but also aftershocks here. So these results are coming from the EMSC. So again, through this Quakelink protocol, as I mentioned, it can handle also earthquake information. And what we see here is the circles. So these are pie charts of the different Did You Feel It information. So the color represents the intensity here. The outer color, or this here, for example, or that's the false value. The outer circle represents the maximum value, which is measured or reported in that cluster of the pie chart. So it's aggregating different Did You Feel It reports. and forms these kind of pie charts, and then we get the percentage of the different intensities which are reported in that area. So it's a nice summary of what is ongoing. The EMSC collected for this earthquake in 14,000 did you feel it reports, so you can't plot them every single. So we tried here to summarize it through these pie charts. So what happens is that the EMSC collects the information, they push it into their local Quakelink server, and there's a Quakelink to Quakelink connection to the national institutes and also to the TURNkey platform, and that collects this information and visualizes it here, or first collects it. Yeah, so these are the main feature of this platform. An important thing was the development of these Raspberry Shakes. So initial development started in 2016. At first with a 1D, so one vertical velocity component. Over the years it was extended. So we have the 1D sensor, we have a 3D, so 3 velocity components, the 4D, which is 3 strong motion components plus 1 velocity. And there's also the shake and boom, which is a combination of infrasound and seismic. So they were designed from the beginning to be easy integrated into the SeisCom framework. So that is the most common seismic processing framework nowadays. So the last time I counted, there are about 500 institutes worldwide which are using SeisCom, and that is also the platform we use here for the TURNkey, for the acquisition and processing part here. So they integrate smoothly into that system. Normally via the seedling protocol, which is also nowadays a standard, but this was replaced, or it's not replaced, it's also still there, but we added this CAPS, so the Common Acquisition Protocol server, which can handle multi-formats and multi-sensor data. So anything which you can attach a time series to can be transmitted with this acquisition system. So we use it for the seismic data, for the GNSS data. We have temperature measurements, we have tidal measurements, there are camera, so all kinds of data is transmitted through the CAPS system here. So that is acquisition system, CAPS and seedling, depending, the testbeds use different, depending on what is the purpose, let's say. So the CAPS protocol allows this earthquake early warning with smaller record sizes, so we have less delay in the data. The seedling, where their velocity or the speed of a detection is not an issue, testbeds still go with the seedling connection. Yeah, so everything is fed into the SeisCom system that is generating the earthquake parameters, and all this again is then handed over by Quakelink to the platform. Okay, I think it's your turn again. Okay, okay, thanks a lot.
Now we talk about the scientific engine that has been developed at NORSAR. So as I said earlier, the engine is using all this dynamic data as well as other data that needs to be prepared during the installation phase of the platform. And it has different components, but the main core of the platforms are, of the scientific engine are these 3 engines. The engines that deals with the early warning, earthquake early warning, and then the engines that deals with the rapid response to generate shake map and the physical and economic impact, socio-economic impact, and the engine related to the operational forecasting. So we have other components, the event listener that listen the event and then basically to send to be sent to different engines about the earthquake locations and the magnitude, and then we have another component that processing, which is processing engines for the different informations or different layers from database to the application programming contacts and the geo server where the information, all different results are sent before it will be visualized in the graphical interface, and also a notification server, which is a two-way communication. So we will go in details one by one of these three main components or three main engine of the platform to explain what is this about exactly. Yeah. Here is the chronological process of the turnkey platforms. So before any event happens, before we mentioned, we have this component that we have added, which we call simulation. The simulation can be used for different purposes. One is like when you install the platform, you do kind of simulation to make sure that all the components that you have added or the choice or the configuration makes sense. But also the simulation can also be used during the exercise. When you do some kind of exercise, and then you can run different scenarios, and then you can see what is your performance for those scenarios. And then it can also be used as a third option for long-term risk mitigation planning. It shows you, for instance, the most vulnerable region, what action you need to do in order to reduce the vulnerability. And then once the main shock starts, then automatically the early warning is the first component that starts functioning. Okay, then it is if it reaches a certain threshold, because each one of these components have the thresholds that is defined. So if it reaches the threshold, then the early warning starts sending the information. Just after, the forecasting also start, because when you have main shock, then there will be an aftershocks. And then forecasting also, it is activated and it starts functioning and receiving data, and then reading this data to generate what we call short-term hazard maps. And then it continues like this within aftershocks, and then once there is an aftershocks, there also the early warning is activated, and so on. So it's like it's a continuous activity that goes along as long as there is aftershocks ongoing. And of course, these aftershocks have, if they meet the threshold that has been defined earlier. So also here, when the main shock starts, and if also the impact of because then we are receiving the ground shaking from the stations, and then if they reach a certain also threshold, then the rapid response is activated, and the rapid response, when it's activated, means that it is generating the ground shaking map and the impact in terms of the damage, the socioeconomic impact, and then it is regularly updated as long as the data is coming. So it continues until the end of this phase of the emergency. So if I explain the main activity of each of these components, so the early warning, so when something happens, then it may send a visual as well audio alert. It is because here we have the instrumental network, and then it is listening. Then when it's reached the threshold, then it's received by the engine, the scientific engine for the early warning. And what is generating the potential impact that may be produced by the earthquakes in terms of shake map. And then here we will have two different maps that can be sent to the graphical interface through the server in terms of big ground acceleration, but also in terms of microseismic intensity, which is the most easiest also way to understand the level of intensity produced by an earthquakes. Yeah. The second activity, the second engine activities is as I said, it starts once the early warning started, then, and if it reach a certain level of threshold, then the rapid response to the earthquake, it starts generating two different data. One data is coming from the observation from the instrument. It's related to the ground shaking data, and then basically it is updating the previous shake map that was generated by the early warning engines. The one that generated by early warning was just as a first idea what could be the impact of earthquakes in terms of intensity. But then they are updated once we start receiving data in terms of the ground shaking. And then it keeps it updated as long as there are data coming from different networks. And then once it's done, then it is using this data to compute the risk and loss. So we get data in terms of damage, the most damaged area, you know what to go from or where to start from. And then potential fatalities or casualties were also to be considered. And also other data like the economic loss, but it's later. But the other important data is the homeless. Then you knows exactly how many charters probably will need in order to take care of this homeless. And then this data is also updated as long as you get data from eyewitnesses. And when I say eyewitnesses report, these are data that comes from the previous smartphone-based tools that are connected, the TURNkey platform, the TURNkey smartphone app that's provided by the first responder or field first responders. They are observing data and then they send it to the platform and then it's updated or it's validated by the decision maker. So this is how all this is kept updated along the time whenever the data is coming. Then for the operational earthquake forecasting, so it's basically looking at the change in the seismic hazard condition based on the conventional or the static probabilistic seismic hazard that exists. So it keeps updating the event catalog that is linked to that event earthquakes, and that basically is using, as I said, the existing static hazard map that you see in, for example, probably you see in the code, seismic code or other documents, guidelines. And then also and then combining this, you basically identify if there is any, the engine identify if there is any increase in seismic probability within the next 24 hours or as long as the data comes. And then basically once this is done, then it's generate this kind of information, the long-term hazard, which is the static hazard, and this is basically what generate as a short-term hazard, means that there is a changes in the hazard compared to the initial one. There is a change, then there is probably potential high or low probability that an earthquake will occur or an aftershocks will occur. And this is show the increased seismicity probability comparing the two. So this is kind of giving an idea what could happen in the coming 24 hours. And then the simulation that I explained earlier. So it's you can simulate, you can select any type of scenario you would like to have, probably an historical scenario, and you would like to know exactly what could happen. And then you can simulate, and then you can generate an early warning for that simulation. And then you generate the rapid response, means that you are generating the impact of the earthquakes. And then you get those results for the scenario that you have selected. And yes, then those results is basically it may have different purpose, as I said, for probably the installation phase or for the risk mitigation planning, as well as for the exercise. And yes, today we will do kind of some kind of demo with a scenario, with simulation, which we'll see how it works and what type of information you get. Now this is just summary about the main features of this scientific engine. So the first one is, as I said, it relates to the short-term time-dependent probabilistic seismic hazard analysis, which means that there is a change in seismic hazard, and it means probably there is a probability that an earthquake may occur or aftershock occur. And here it's, as I said, is a combination of seismicity rate that was computed using seismic and non-seismic data. So they use this result, the engine uses this result combined with the integrated conventional or static probabilistic seismic hazard map, and then they will generate this, and based on this, the outcome of this, they will tell you the level of probability that an aftershock happens. And then the second main features, it's the fact that it allows this rapid mapping in near real time. So as long as when earthquakes happen, so the engine, the rapid response engine, generate the map of damage, generate the map of fatalities or casualties, and also shelters, the safest area, and other information related to emergency action. And then it kept updating it as long as there is data coming from seismic network stations and data that comes from the eyewitnesses, means from the first responders who are on the ground. They are communicating through the TURNkey app, telling that, for example, in this area, your map, it says there is no damage, but actually there is a damage, update it. So he sended it, it's approved or validated, and then the map is updated, and then we got a new map. And then this process continue as long as there is a continuous in data that fits the platform. And then finally, which is another interesting feature, is related to building a specific multi-criteria decision support. So when earthquake happens, when it generates shock map, it generates damage, but then the platform helps in taking the most optimal action, mitigation action, based on defined actions or preference of the stakeholders. So here, basically what Gemma was mentioning in her previous slide, previous presentations. So it is integrated here in order to help for a quick decision based on cost-benefit analysis, and also based on the preference of stakeholders. So this is the three main features of the engines. I think now the next will be my colleague or my friend Alberto from Data IT will explain the last part of the platform, which is the graphical. And this is what, as the stakeholders will see, is the yeah. Oh, where is it? It's gone. Oh, I don't know what's happened.
Can you go back?
All right,
okay. Otherwise, you do all the job. But I will be very, very fast, because today in the afternoon we will have the chance to see the platform working, and we will see a simulation on how you can use this platform and what benefit this platform can bring. So in the afternoon, I will have the chance to explain in detail all the functionality, and I don't want to bore you now giving again the idea. Just an overview for now. So we have realized two different kind of interface. Just before continuing, I am from an Italian company, and we are not specialists in earthquake. We are specialists in creating a command and control room for rescuers. In particular, we deal in Italy with 112 services and emergency medical services and firefighters. And what we know is that we have to create systems that are easy to use, rapid to use, and the effort we make together with NORSAR was to create something simple, something usable. And the idea was to create two, let's say, two components. One is, I don't know the cloud-based user interface. This is a sort of interface, is the interface that the control room could use to understand what is happening and take decision on what is necessary to do. And so when there are a new earthquake, there are the early warning messages, but also there are an indication on suggestion on what behavior to do, on what information to send and to whom. And this is the idea. And so the other part is the mobile application that has a double role. On one hand is to give an overview of what is going on, but it's very simple. I mean, there is an earthquake in this area, this is the extension of the earthquake, and etc. The other one is to support rescuer. What are the functionality? On one hand, you can provide observation to the control room. So you are on field, you see that the hospital has damages, you can make a picture of this hospital, you can say what is, in your opinion, the damages that you have received, and this is the one that will be received to the control room first, and then by the control room it will be validated, and then it will go to the engine, and it will be re-elaborated and will provide the support to modify the suggestions. And the other one is about the early warning. The early warning is implemented for the rescuer only in case of aftershock. Why? Because since we are talking no more than 3 or 4 seconds, it is before an earthquake, before a main shock, this will not give support because you will not aware of what to do and you will forget. But in case of aftershock, so you are on operation, you are aware that that could happen an earthquake, you are on mission, this can be useful. And in this case, you will, in case of an aftershock is coming, you will receive an alarm, your mobile phone will start to ring, and you can provide help, support, or request for help, or request that, or information that you are safe. The functionality are a lot, and we will go in detail in the afternoon. So the demonstration will last more or less 1 hour. So I mean, it's not the case now to be very, very long. Just what are the main features? So we provide a situational report. I think, in my opinion, the most interesting functionality is related to the rapid response. In a sense, when there is an earthquake, the first things that you have to understand is what's going on. And with this application, you have suggestion on the potential damages. In the opinion of the engine, I mean, based on the software that has been described today, there are some building, and so you will see this building is considered highly damaged. This is not highly damaged. This hospital needs to be evacuated, and so on. And so you can go fast in do the operation faster. Then there is the double-way communication and internal procedure activation. What is this sense? They are connected. So the task that you have to do is suggested and say, in this case, you have to do these things, this thing, this thing. And on the other hand, the communication, you may be, for your procedures, may require to send communication, and this communication can be triggered in an automatic way or in a semi-automatic way. This means that the communication is prepared, and then, okay, you validate it, and then you push the send button. And we have discussed already of the eyewitness observation and aftershock alert of the mobile app. Okay, let's go at the last, it's finished, okay, it's finished. Okay, let's see you in the afternoon, okay.